Here we are for intermolecular forces. This is the last section in our bonding unit here, and we're looking at the forces that are occurring in between covalent molecules primarily. So polar covalent and nonpolar covalent molecules. So the ones with below 50% of ionic character. So these things, there's bonds within the compound, but then the individual compounds will have reactions with each other. And we've talked a little bit about polar, whether the bonds are polar or nonpolar, but now we're going to look at whether the molecule is polar or nonpolar. So here's our first example. So in this we have hydrogen. And hydrogen, when it bonds to itself, if you remember our discussions on bond polarity, they both have an equal electronegativity. So the difference between their electronegativities is zero. So they both have an equal pull on those electrons. When there's an equal pull, well, then the electron cloud is distributed uniformly around the nuclei of those elements in question. So there's no overall bond polarity. And if there's no bond polarity, if the bond is nonpolar, well, then the molecule has to be nonpolar. Okay, if there's no charge difference within any individual bond, well, then the compound has to be nonpolar. Okay, now though, say we have something like this, hydrogen fluoride. Here we definitely have a hydrogen that has a 2.1 and a fluorine that has a 4.0. I mean, this is such a high electronegativity difference that we'd almost consider it to have significant ionic character. So what's happening here is that electron cloud, this is a polar bond, and that electron cloud is being pulled towards the fluorine. So that results in the fluorine being partially negative and the hydrogen having a partially positive side. So not only is this a polar bond, but because that charge can concentrate on one side of the molecule, it is a polar molecule. Now, with that being said, not every structure with polar bonds is going to result in a polar molecule. Here's the classic example for one that doesn't. It's CO2. Now, CO2 has a carbon in the middle. Carbon has an electronegativity, I believe, of about 2.5. Oxygen is 3, so there is bond dipoles in this compound. So electron concentration being pulled towards that oxygen. It's also, though, being pulled in the opposite direction. When we have charge concentration being pulled in opposite directions, they cancel out and there's no net dipole, or even though it has polar bonds, the molecule itself is not polar. And so if we have a symmetrical molecule where all the bond dipoles cancel out, then we have a non-polar molecule overall. So the essential thing to know is, one, we have to be able to look at the electronegativities to calculate if it's a polar bond, but then two, we need to know what the geometry is. So that's why it's essential to know our Vesper theory, to know our valence shell electron pair theory really well, so we know the shapes of these molecules, because if it has a different shape, for instance, water has a net dipole and a strong one at that. So what's the difference between these two molecules? Well, the true difference is that water forms a bent shape, where CO2 is linear. This water molecule, remember, it has 4 negative charge centers. So really, this isn't drawn. It's a nice three-dimensional model, but what we have to remember is that oxygen has those lone pairs. Remember, it has lone pairs. It has 6 valence electrons. So when it bonds to hydrogen, and we make water, yes, it has these 2 bonds, but equally important to the geometry of the compound is these 2 lone pairs. And remember in Vesper theory that these 2 lone pairs actually push those hydrogens down more so than even bonds would. They take up a lot of space and they repel each other and they repel those hydrogen bonds. So instead of having a linear structure, knowing Vesper theory and knowing that lone pairs take up room, we result in a shape that's called bent. Again, it has tetrahedral geometry, but the shape is called bent. So now, when we have that oxygen that has an electronegativity of 3.0, and the hydrogens that have electronegativity of 2.1, now we have bond dipoles here and here, and now they're both pulling towards the oxygen, and they're not at equal opposite directions. They're actually kind of overall going in the same direction. So notice, overall, they're pulling towards their left and right poles might cancel out, but overall they are pulling charge concentration towards that oxygen. So that oxygen ends up with a partial negative charge, and the hydrogen side is partially positively charged. So notice, again, we already looked at carbon dioxide. Remember, these poles are in the opposite directions. So really, the overall net dipole kind of cancel each other out. If we look, notice the bonds are polar, but the molecule itself is nonpolar. If we look at another example, carbon tetrachloride, it has 4 chlorine molecules. Again, in 3 dimensions, it has is sp3 hybridized. It has tetrahedral molecular geometry. It's a tetrahedral shape. Chlorine has an electronegativity of about 3.5, whereas carbon, again, is like 2.5. So there is a charge difference. Electron density is being pulled out towards this chlorine, being pulled out towards this chlorine, being pulled out towards this chlorine, being pulled out. So there's a lot of bond polarity. These are both molecules that have polar bonds. However, they both overall are non-polar molecules. So we have to know the difference between a bond polarity, one individual bond, or molecular polarity, which is looking at the shape and the bond dipoles. So in this case, yeah, they're pulling opposite from each other, but because this is a symmetrical molecule, all those pulls are canceling each other out. Here's water again with its bent structure, so that charge is concentrating on the oxygen, and there's a partially positive side where the hydrogen is. Notice just one more example. Notice the sulfur dioxide, and notice sulfur dioxide is also, has trigonal planar molecular geometry because of the 2 bonds and the lone pair, but that ends up in a bent type of shape where the oxygens are more electronegative than the sulfur. Again, oxygen is about 3.0. Sulfur, what's sulfur? Sulfur is about 2.5, so there is electronegativity difference, and because of the bent structure, those electrons can be concentrated on the oxygen side, and the sulfur side ends up being partially positive. So these compounds are polar molecules, and they have what we call a molecular dipole. Here's a few more examples. Hydrochloric acid has a dipole. Ammonia has a dipole. The charge concentration is pulled towards nitrogen. Again, nitrogen has a lone pair. That's why we see this trigonal pyramidal shape. Again, tetrahedral molecular geometry, but a pyramidal shape, so that charge can concentrate on the nitrogen because those hydrogens are bent down. BF3, though, is symmetrical. It has 3 bonds that are all 120 degrees apart. They're all pulling in equal opposite directions, so they cancel each other out. They have polar bonds, but it's a non-polar molecule. Non-polar molecule here, carbon tetrachloride. But here's an interesting thing. If we replace 3 of those chlorines with hydrogen, now hydrogen is less electronegative than chlorine. Hydrogen is actually slightly less electronegative than carbon, so the pull is actually now in from hydrogen towards the carbon. So the electrons get pulled towards the carbon and then out towards the chlorine. So now by changing the location, or what's bonded at those at each of those ends on the carbon, now we've changed this into a polar molecule. So the symmetry is not just the shape. Tetrahedral compounds are not always nonpolar. It depends what's bonded to them. If there's, again, it has to have polar bonds, and those polar bonds have to not cancel out with poles in opposite directions. Now, when we have those polar molecules, again, we have non-symmetrical molecules that have polar bonds, so we have overall dipole moments. What can happen is then those compounds are going to act like little magnets, and they're going to stick together. And so with water, we have a certain kind of sticking together called hydrogen bonding. This is an intermolecular force. It's intermolecular because it happens between molecules. So it's not an actual bond. It's not an ionic or covalent or metallic bond. It is an intermolecular force. It is a bond between molecules. So it's not as strong as a full bond. It's not as strong as ionic bonding. It's not as strong as covalent bonding or metallic bonding. But it is a force. It is, we call it hydrogen bonding. And so notice what's happening here is the positive sides of the hydrogens are sticking to the oxygen, the partially negative sides of other water molecules. Now this force is significant. It's not one that we just want to say, there's hydrogen bonding. Hydrogen bonding completely changes life as you know it. If there was no hydrogen bonding, life as we know it actually would not exist. Water is amazing because of its ability to hydrogen bond. Probably the most important characteristic is this. If we look at, this is down the column that oxygen is in, group 6 elements, hydrogen bonded to tellurium has, notice, a boiling point below 0 degrees Celsius. Hydrogen selenide, notice a slightly lighter molecule, has an even lower boiling point. Hydrogen sulfide, a lighter molecule, has an even lower boiling point. So typically, the boiling point of a compound goes up as its mass goes up. However, look at this crazy, crazy peak for water. Water boils at 100 degrees Celsius. Why does water, the lightest of the series, have the highest boiling point? Well, water has a high boiling point because, because it has hydrogen bonds. So those other compounds, they're still non-symmetrical, but those other elements aren't as electronegative. They can't pull the electron density away from the hydrogen like the oxygen can. So these hydrogen bonds, to boil water, we have to break these hydrogen bonds, and that takes a tremendous amount of energy. Much more energy than just putting that into the gaseous phase, and we can see that on this chart. We can see how dramatic of an influence that has. Now notice this, not every compound that has a hydrogen, and even an electronegative element, is going to have hydrogen bonding that's going to have this effect. It has to be a very electronegative element, and that electronegative element also has to be very small. It has to have a good ability to pull that electron density away from the hydrogens. So we actually see that in water. Notice we see that with hydrogen fluoride, and we also see an elevated, although not as much, but we also see an elevated boiling point in ammonia. Notice methane, we don't see it because methane is completely symmetrical and completely nonpolar, and so it follows our general trend for boiling points that increases as its mass increases. The ones that are off the chart that kind of break that trend are the ones that exhibit hydrogen bonding, which is such a strong force again. It really makes these compounds act as if the things that were much, much heavier, because they have all these intermolecular connections, again, that have to be broken in order to boil these. And not only does it affect boiling point for water, not only does hydrogen bonding affect its boiling point, but it increases water's surface tension. It increases its specific heat capacity. It increases its enthalpy of vaporization. It increases all of these properties for water that otherwise life couldn't exist unless if water had its boiling point down here below -100, all the water would just be in a vaporous phase on the planet of Earth. On the planet of Earth. On any planet, actually. So it really makes life happen. And there's other crazy properties as too that water has that most other molecules don't have, like adhesion and cohesion. And those are actually talked about in a great crash course that I'll have you watch here. But we want to focus on just the chemistry aspect. So hydrogen bonding can occur between just 3 elements bonded to hydrogen. It occurs with oxygen bonded to hydrogen, nitrogen bonded to hydrogen, and fluorine bonded to hydrogen. Again, the reason it's just 3 elements is because these elements have very high electronegativities, and they're also very small. And think about what happens when these pull electron density away from hydrogen. The one reason it happens only with hydrogen is hydrogen only has 1 electron of its own. So if oxygen pulls electron density away from hydrogen, basically we have a bare proton there. So this partially positive charge is much, much stronger than we might see in any other ordinary dipole. So these things will stick to each other, just like it's showing here, but they'll stick to themselves, I should say, and they'll stick to each other. So ammonia will hydrogen bond with water, or water could hydrogen bond with hydrofluoric acid. Really amazing, amazing strong intermolecular forces. Really, however, hydrogen bonding is really essentially a dipole force. It is really any generic dipole force where we have a positive and a negative side of a molecule and they're sticking together. That's called a dipole attraction. And really hydrogen bonding is just a dipole attraction, but it's such a strong dipole attraction that we give it that other name of being hydrogen bonding. If it's something where hydrogen is bonded to something else, or it doesn't even have to be hydrogen, if it's just 2 molecules that have a dipole, but doesn't involve hydrogen and nitrogen, fluorine or oxygen, well then it's just a dipole attraction. And they're still going to stick together. They're still going to have, some characteristics of dipole interactions. They're still going to have slightly higher boiling points and things like that, just not the extreme differences that we see with things that can exhibit hydrogen bonding. So we have hydrogen bonding, we have normal dipole interactions. Last one we look at is what's called van der Waals forces, and hopefully I can spell it van der Waals, and I think Waals has 2 A's in it. So van der Waals forces. Van der Waals forces are the forces that are exhibited between molecules that don't have dipoles, nonpolar covalent compounds, mainly between gases like hydrogen gas and oxygen gas, or noble gases, neon, argon. So what we'll see with these is even though they're completely nonpolar, there's no charge concentration. Randomly, what happens is that the electrons are in random motion. So at random times, the electrons will congregate on one side of that compound, or gas, if it's a single element. When that happens, it will induce a dipole in the element next to it, and it will cause them to kind of slightly stick together. So these are called van der Waals forces, or sometimes they're called dispersion forces, or induced dipole interactions, but they're randomly induced. So it's just the random motion of electrons. Electrons randomly congregate on one side of this compound, making the other side positive, which influences the other molecule next to it to become a dipole as well, and so they stick together. A very, very weak force, but this is why when a gas is released, the gas cloud will kind of stick together before it just fully disperses. So it reduces the rate of dispersion of gases as van der Waals force. So these are our threes. Dispersion forces just do the random motion of the electrons. Stronger than that would be our dipole-dipole interactions that happen between any polar molecules. And finally, hydrogen bonding. But hydrogen bonding, again, really only occurs if we have hydrogen bonded to fluorine, oxygen, or nitrogen. And again, mainly in the biggest instance of this is with water. This is the one we really want to focus on for hydrogen bonding. So one thing we have to remember, again, is if we look at intermolecular forces. Now, what type of intermolecular forces is something going to have and why? Well, if it is an ionic compound, well, it doesn't have intermolecular forces. All it has are ion forces. It has its big lattice structure. And so remember, even when we're looking at these intermolecular forces, ionic bonds, covalent bonds, metallic bonds are all stronger. Real bonds are all stronger. These are intermolecular forces within covalent compounds. So it can only happen in covalent compounds. If we have a covalent compound, we need to look at the Lewis structure, and we need to look for polar bonds. Now, are there any polar bonds? If there are, then we have to look. So there really should be more steps. At the Lewis structure, we'd ask ourselves, are there polar bonds? If they're polar bonds, then we'd have to say, is the molecule unsymmetrical? If it is unsymmetrical and there is polar bonds, then it can be a polar molecule. So then we'd say yes. Now, if there's nitrogen, oxygen, or fluorine bonded to that hydrogen, then there's hydrogen bonding. If there's not, but it's still polar, then it has dipole interactions. If it is not a polar molecule, doesn't have hydrogen bonding, then it's going to experience van der Waals forces, or there's a couple different names for it. Induced dipole is a name for it, London forces, van der Waals forces. There's actually a lot of different names for this same effect. So here's a chart, and this has a little bit more detail than what we looked at. But notice, ionic bonding is definitely our strongest type of bonding, followed by covalent and metallic. And metallic and covalent can overlap a little bit. It depends on what structure we're looking at. Below those are our intermolecular or non-bonding forces. So hydrogen bonding is really our strongest, so we can ignore these other ones like ion dipole. It's really just a hydrogen sticking to a dipole like when salt dissolves in water. So we have hydrogen bonding, followed by dipole-dipole interactions, followed by our London dispersion forces. And notice there's a few other variations of dipoles or induced dipoles, but really for intermolecular forces, these are the three we want to look at. And this is the relative strength. So all of these things, even the vast strength of hydrogen bonding, is still weaker than a metallic, covalent, or ionic bond.